So I'm very, very happy to be here today. When I originally submitted my talk abstract, I wrote something incredibly generic, and so I hope you bear with me as I talk about something hopefully significantly more interesting. I know that the audience here is engaged and interested in data processing, and I'm assuming you have a bit of awareness about Spark. And so what I'm going to be talking about is how Spark can fit into realistic machine learning workflows. So there's lots of great material out there on how to use Spark in isolation. And what I'm interested in talking about today is how, if you're a data scientist who's building machine learning models, how Spark can realistically fit into your workflows currently. So both in model training and model deployment. And hopefully you'll find some powerful, useful things in here, or at least some funny jokes about pickles. So Spark is a huge project. I would say Spark is in fact an ecosystem, much like this rainforest, where we have core Spark, which is an in-memory distributed computational engine, and other pieces of Spark that work together to support a lot of different use cases. So we have things like Spark SQL, which is pretty close to core Spark at this point because some of the most flexible, useful, well-written parts of Spark rely on Spark SQL. There's things like Spark MLlib, which we'll talk a little bit about today, which is a machine learning library that's built inside of Spark with some algorithms that are available to you already, which depends on Spark SQL. Spark Streaming, GraphX, I think we've heard these things mentioned at different talks throughout the conference so far. So there's a wide ecosystem of what you can use Spark with and different use cases you can use it in. I'm going to do a brief description of what the Spark execution model looks like before digging into what a real machine learning workflow is and how Spark might fit into that. So the Spark execution paradigm is that you write a Spark program. That Spark program gets executed on a driver. A driver is a node that's near you. It can be an edge node of a cluster, or it can be your own laptop. That driver program creates a Spark context, and the Spark context is what is used to interact with and orchestrate the rest of the worker nodes, which are worker nodes that are actually executed on the cluster. So the worker nodes spin up executors, which are the processes that are going to do work on the cluster for you. And those executors are going to have parallel threads working, which are going to operate on tasks. This might be splits of the data, so you might have a huge file inside of Hadoop or S3, and that's partitioned into blocks, and you'll process those as tasks separately. A use case that I'm going to talk about is doing massively parallel model fitting. And in that case, you're using the same input data, but you have multiple processes because the actual process of model training is going to be slightly different between each of those tasks those executors are performing. So that's very briefly the ecosystem that Spark exists in and the Spark execution model. Now, what I think is a little more fun than, and this is my bias of having a background in mathematics, then what I think is a bit more fun than just talking about the platform that Spark provides is what is the real thing that we're trying to do? What is the real thing that we're trying to build? So let's say that I'm hypothetically a data scientist and I want to build some sort of predictive model. I usually have some amount of historic data. That historic data exists in a database somewhere. I'm going to do some sort of process that then generates a model. And if I want to use that model ever again, I'm probably going to need to save it somewhere. So in this diagram, I've colored blue-green the pieces of it that are data that is written somewhere. And the white blocks are the processes, so it's some sort of computational process that happens. So model training is almost vacuously defined as the thing that fits historic data together with your model that you actually write down somewhere. And then once we've trained this model, we don't just pretend it never existed and go away, right? We want to deploy this into production. We actually want to use it in the real world. So part of my introduction was that I lead data science for the engineering team at Cloudera, but a previous role that I had at Cloudera was interacting with our customers and trying to advise and guide them on how to take their current practices and fit that in with different tools they might be interested in exploring, or just generally advise them on how to build good production systems if they're trying to get their data science team to a certain place. And so a fair amount of this advising was focused on what it means to productionize a model. And what I've realized is that when people or companies talk about productionizing machine learning models, they can mean a huge variety of things. And so the reason that I have these like star call-out boxes for new data and model results is that I've seen a variety of ways that this shows up. So this could be, new data could be coming into your model scoring system through a REST, like an HTTP request, a REST call to a REST server. It could be that you have a nightly batch job that gets executed on a database and you're writing a file out somewhere. I've seen both of these use cases called putting things into production. And so when it comes to fitting Spark into this workflow, you have to both think about how you're persisting your model and what two pieces you're trying to connect, what the new data is and what the result is going to be. So this is just a very generic sort of workflow, and I'm going to talk a little more concretely about what it means when we have more specific pieces that fit in here. But first, I want to focus on this model training step. Did you like how I just sort of pointed at this and I was like, model training? Simple. I want to zoom in a little bit on the model training step. So frequently, when we have historic data, the first thing we're going to do is we're going to take our data, we're going to take a small percentage of it and set it aside and not look at it until we think we're done. And we're done with our model, right? So this is going to be our completely blind to us test set. Then we're going to have data that is our training data. When we take this training data, we're going to do some sort of maybe pre-processing, change this raw data into features that get fed into a numerical algorithm that estimates parameters in a machine learning model. And those series of steps combine together to be this machine learning pipeline or model generation step, where at the end of that, we have this model that we can write out somewhere where we say, well, when I get data in, I tokenize the strings, and then I do TF-IDF, and then I do some sort of classification on this text. And from those series of steps, you can fully describe what it means to both train the model and to actually apply that model to new data. So we'll describe those pipelines, we'll fit any sort of estimated parameters we need in there, and then we'll write out this persistent model somewhere. And we'll want to usually do this in a both iterative way where we're testing and doing cross-validation on that training set that we have until we get to a point that we feel pretty good that the evaluation metrics that we're using for our models are performing well. So this could be any number of things. It could be the precision, the recall, the area under the precision recall curve, the area under the receiver operator characteristic, right? Choose your favorite one, but there's some sort of evaluation that you're doing and usually some sort of cross-validation. Beyond that, when you're describing these models, you usually also have these hyperparameters that can describe what the model training is and what it looks like, right? And so this is not a single step where you say, okay, I've fully described the best model. I'm going to run it once, see what the statistics are, and say, like, yes, sure, this evaluation metric is good enough for me. Usually you continually refine your model until it's at a place that you need it to be in terms of precision or accuracy, whatever it is you need. So these multiple steps, so the featureization, the model training, and then being able to take that and do, say, cross-validation or grid search with it, requires pipelining. And so pipelining ends up being a really important concept in various machine learning libraries, and it's one that a lot of APIs built for machine learning have moved towards. And so that is very, very related to being able to do cross-validation well. So train your model in one way and then know that you're applying that same trained model on your new test set. And that ends up also being incredibly useful and valuable in production. So I know a huge number of data scientists and data engineers at various companies that built data products, that if there's a split between the data scientists and the people putting machine learning models in production, they run into this issue where a data scientist will make a model and then they'll put the wrong one into production. So being able to validate that the thing that you actually made is the thing that is getting run is a valuable thing, because it's a mistake that you're like, oh, no, no, no. When I talk about a model, I know it was that model. Being able to identify it and know that the thing that you made is the thing that gets run in every situation is actually challenging. And so that's why a lot of these APIs end up trying to focus on this pipeline concept and making sure that the thing that you fit is the thing you're actually applying. So talking about generics is all well and good. I will try not to be super generic and instead now get a little bit more concrete, because I think getting the abstractions correct for machine learning ends up being a big mouthful, and it's a lot more interesting to talk about something realistic. So the realistic thing that I want to talk about is customer churn prediction. So I like this for a few reasons. And the primary one is it's relatively easy for me to explain, and I'm a pretty lazy speaker, so I'm glad that I just get to briefly explain this to you. And the second one that I think is also important and valuable is this is a problem that I've done with Cloudera's customers a few times. It comes up again and again. It's ubiquitous. If you have any kind of subscription model, people are interested in churn prediction. So let's say we have 3 customers. We have ex-President Barack Obama, we have a child, and we have a baby with a phone. And we want to know if next month these customers of ours are still going to be customers of ours. So the ex-president will still be a customer of ours, the young girl will still be a customer of ours, but that baby doesn't need a phone line, so it's going to stop paying us, right? And we should be able to predict that. And so the example that I'm going to use is from the UCI machine learning library. You can go get this data set if you want. I have some code examples online, which if you ask me after the talk, I can point you to for some of the things I'm going to point out, but I don't have it all implemented for exactly this problem. I have it for some of it, so ask me about that later. This data set's pretty simple. Each line is an individual, it's a customer of ours. We have information about what US state they're in, their phone number, whether or not they subscribe to an international plan, how many minutes they've used, day, evening, night, a bunch of numeric values, a bunch of categorical values, and then the very last column is whether or not they churn or not. So this is a very straightforward supervised learning problem. We have labels, we want to be able to predict these labels and test that we're doing well in the future. So we're going to make some pipelines. This data set is not very large. I can download it very easily over the internet from the UCI machine learning library. So the first thing I probably want to do is just use scikit-learn. This is realistic, right? This data set fits in memory. It doesn't take that long to train a single model for it. And so what I'm going to do is I'm going to use a gradient boosting classifier. These things tend to perform really well, and scikit-learn already has it implemented, so that's great. I have some magical function called getData, which returns to me x, which is all the feature vectors, and y, which are the labels that I'm going to try and predict. From there, I'm going to create a gradient boosted classifier, split my my data set that I'm training it on into a train and test split for this particular instance of building a model. And then I'm going to fit the model to the training data, apply it to the testing features, and eventually get some sort of evaluation metric of how well my model performed. This is all well and good, and you can see 2 very pertinent things about this gradient boosted classifier. It has a function called fit and a function called transform. And transform doesn't make any sense to call until you have fit the model. So this is exactly what defines a pipeline, or a thing that has a characteristic of a pipeline. It has a fit method and a transform method. This almost makes sense, except if you go back and look at the data set, there are categorical variables I haven't really dealt with. There are these labels that are true and false, which actually in the gradient boosted classifier, it's expected that there's zeros or ones. And so there's processing that I need to do in order to actually get it to a stage where I can use this gradient boosted classifier. So instead, I'm going to create a pipeline which has these steps in it. So in this pipeline, I'm going to get the data. I'm going to do things like one-hot encoding, where for categorical variables, if I have, say, 50 different possible values for each of the US states, I'm instead going to create a vector that gets appended to this feature vector that is either 0 or 1 depending on what value it's taking. So it's kind of like a pivot table, but like a binary pivot table. And then I create this pipeline that says, okay, I'm going to take my input vector, I'm going to transform it in this way, I'm going to fit this model. And this pipeline, you can see I'm doing exactly the same thing. So where I had just the machine learning model before that had that fit and transform method, this pipeline now has the fit and transform method. And so I can use it very easily here. Great. Now, Spark MLlib. Spark MLlib has evolved quite a bit in the last year or two. And at this point, Spark MLlib has taken a huge amount of inspiration from the scikit-learn API. Spark MLlib similarly relies on pipelines, where the thing that you create, this pipeline, is a series of steps and operations on your data, and this pipeline has both fit and transform methods. So this is just an example that's a screenshot from their documentation, where people are trying to create some sort of classifier on text, and they have featurization steps like tokenizing, so going from a string to a collection of words, hashing, so going from a collection of words to a feature vector, and then going from a feature vector to a fit model that has parameters in it that can tell you whether or not a certain feature vector is of one type or another type. So an interesting part of MLlib, like I mentioned, is that MLlib lives in this ecosystem of Spark, and the newest version of MLlib, which is confusingly moved from the MLlib package to the ML package, is that it fits in and integrates very closely with Spark SQL. And so all of your operations in your pipeline are transforming columns in a Spark SQL table, which is basically a data frame-like object that is a distributed data frame that Spark is operating with. So in this ML pipeline example, I create these transformers, which is these string indexers. So this is, again, a one-hot encoding kind of thing, where we're taking whether a label of whether or not they're churned or not, whether or not they're international, they have an international plan or not, and then creating a feature vector with this vector assembler, and then fitting a decision tree classifier. So at the very end, we create this pipeline that has stages in order where we do some featurization, like indexing those categorical variables. We assemble them into a feature vector, and then we have a classifier. And so again, we're just defining these pipelines that we can use in a few contexts. So I did it very manually in the sense of it doing a test train split in previous examples, but you can imagine that this pipeline concept allows you to do cross-validation very, very easily. So now that we've defined these pipelines, we can train these models, we're going to deploy them. Great. But what does it mean to deploy it? There's a few things that fit into a discussion about deploying a fit model. The first is how you've persisted that model. You don't just sort of fit a model, have it in memory, and feel good about that, right? It's not an abstract concept where once you've seen the evaluation metrics, you're like, oh yes, this is a thing that exists now, right? You actually need to persist and write down that model somewhere. And given that you've written down that model somewhere, you need to be able to read that model again in your model scoring system. And that model scoring system could be a number of things depending on what you expect your input data to be and what you expect your output data to be. So let's talk about persistence. First question is, how did you save your model? You have a few options. People that are already familiar with Python have probably heard of pickle or joblib. these are ways of just dumping Python objects into bytes and being able to read those bytes back again. There's a format called PMML, which if you have a visceral reaction to XML, it's not going to make you feel good, but it's incredibly consistent. It's more human readable than a pile of bytes, and it doesn't have a lot of the flaws that I'll talk about with respect to pickles and JobLib. Fourth option is to do something custom. Custom is feasible. A lot of people do this. It is very challenging, and before you go and do something custom for your model serialization, I would strongly encourage you to look at the pros and cons of pickling, JobLib, and PMML, because these are systems that people have thought about a lot and written about the trade-offs in them, and seriously take those into consideration before you build a custom system, because they have listed very well the types of issues people run into. So there's this really great talk, if you use Python a lot, that's called Pickles Are for Delis. And it's from PyCon in 2014, I think, where an engineer talks about some of the issues that pickling objects presents. So pickling an object basically means you open up a file handle, you say, hey, dump this object out over there, and then it does it. And later on, you can unpickle it by saying, like, hey, here's a file. Give me that object back. There's a lot of issues with pickling. Whoa. There we go. There's a lot of issues with pickling. First of all, it's not secure at all. It's very easy for a malicious attack to be put into a pickled object. There are very funny examples of this that have been put online where it's like, look, if you pickle and unpickle this thing, it'll delete all the files on your computer. Like this example that we put here asks for you to confirm each file that we're going to delete, but if you changed one letter, so it's not secure. It's not portable. So pickling an object is very dependent on the CPU architecture you're actually working on. And so if you were to take this pickled file and move it to a different computer, you don't have a guarantee it would continue to work in the way that you would expect it to, which seems like a drawback to me. Similarly, pickling objects can be very big, like much larger than you would expect the serialized object to be. And because of that, it can actually also be very slow. This is something that JobLib kind of works around, the big and slow part, but not that well. It still has issues with security and portability. Similarly, the portability issue comes up with using two different versions of Python or having two different environments of Python on different machines. You don't really know if these things are going to perform the same way. So pickling is problematic. I personally would not recommend it for production deployment systems. You could do something custom, but I want to talk about something concrete, so we're going to talk about PMML instead. And I don't have the visceral reaction to XML that a lot of people have. I think it's fine. It's very consistent. You can kind of read it. It's a little horrifying. Files are a little long, but it at least doesn't have the issues that pickling does. So we can store models as PMML. It's relatively easy to do this. This is something a lot of people want to do, and so there are a lot of libraries that either exist out there that exist out there and integrate with scikit-learn, or inside of Spark MLlib, so there's some functionality for certain types of functions to export them as PMML. So at the top line in MLlib, if you have the right combination of types of machine learning models, you can just say, hey, to PMML and give it a file handle, and it'll export a PMML file for you. Similarly, there's outside libraries that integrate with Spark MLlib and will export more things that are built into Spark MLlib's PMML export functionality. Flip side of this is that there's also outside libraries for scikit-learn that will allow you to export scikit-learn models as PMML. As you might have noticed, I was saying if you have the right type of machine learning function in Spark MLlib, you can export it as PMML. This is the very long list of available functions. And so I think one of the more obvious drawbacks of Spark MLlib is that in general, there's less models available to you than there would be in a lot of other systems. And then when it comes to certain functionality of MLlib, there's even smaller collections. So these are the only models you can export. So the example that I had where I was using a decision tree, which I mean I wouldn't actually use in production anyway, but the example that I had, I wouldn't even be able to export in PMML because it's not supported here, though there are some outside libraries which might allow it. So great, we have an understanding of how a machine learning modeling workflow works, and now we want to see how Spark might be able to fit into this. Actually, I don't know if you all want to see it, but I'm going to talk about it anyway. So the modeling lifecycle, we're back here again, and what we're interested in distributing, in this case, is going to be model training. And so particularly in the model training lifecycle, the thing we're going to distribute is the model fitting. So this is the type of situation that you run into, and it's sort of a classic application of MLlib, where what we have is our historic data is very large. The input data that we want to train our model on is huge. It exists as a huge pile of files on S3 or somewhere in our Hadoop cluster. And our model pipeline, we want to be in MLlib and be able to distribute and have all of this data used to inform our estimates. So what this looks like is what I already showed you. It's relatively easy. We have pipeline stages. We execute these pipeline stages. We can do cross-validation. It'll report metrics to us. This is the example that I have online. It's very accessible, and you can ask me for a link later. Great. We can fit a big model. There's plenty of people out there that will explain to you in great deal how to use MLlib to fit a big distributed model. What else can we do? How else can Spark fit into our machine learning workflows? Well, it can fit into model training again, but slightly different way this time. When we're doing model training, we're really doing that process of fitting a model and evaluating it, and again and again and again, but with slightly different parameters each time, right? As we iterate, we're changing some things to see if we're going to produce a better model. So when we change these things, like the type of, like if we want to do lasso or ridge regression or use some sort of smaller different hyperparameter, we're going to need to produce a bunch of these models. And we can do this serially. Thanks for the light chuckle. That's all I expect out of a slide about cereal boxes. Where one after another, we're going to fit these models. And what that ends up looking like is something like this, where we have grid search CV, which is basically, hey, scikit-learn, I want you to do cross-validation and give me some of these evaluation metrics for my model. And I'm going to give you a bunch of parameters, and you should figure out every combination of parameters and test them all. So in this one, I just have two different loss functions that I want to compare. But you can imagine that as you begin to have more parameters that you want to compare in each of these types of parameters, you get the cross product of all of these combinations, and it ends up being quite a bit of work to do this search. But let's start with two. And so we need to fit these two models. We again define some pipeline that we want. And so here I'm just using classifier again to make this slide short, but it could be a much longer pipeline that I've described. I put in this grid search CV. I tell it what my parameter grid is. It's like, hey, here's a list of parameters I want to try out. Tell me what happens after this. I fit it, and then after the fitting on this grid search CV, there's an attribute called best estimator, which will tell you which one of these models actually is the best, which collection of parameters combined with your pipeline produces the best results. Fantastic, but kind of slow, especially if we have hundreds or thousands of these things that we want to search through. So perhaps we can run this in parallel. Like, I'm not even talking about a cluster. I mean, we just have a single node. What if we run these next to each other? Well, in Python, it's possible to have parallel execution on a single node, and it is somewhat gnarly. There's this horrible thing that people like to not talk about called the GIL, the global interpreter lock. And I shouldn't call it horrible because it prevents a lot of other problems we could run into anyway. But there is a way to keep a lock on the interpreter and trade that between processes. And that is what happens. You can get scikit-learn to do this. And what we end up doing in order to actually use it has nothing to do with us having to have any knowledge of the global interpreter lock. But it does require us to know that, okay, we have these parameters we can set, which is n jobs, which is basically how many jobs in general do you want to have running. Wait, let me think about this. How many do you want to have running how many jobs do you want to spawn overall? And then pre-dispatch is how many you want to spawn simultaneously. So you'll start 2 at a time, you'll do 10 overall, and then within those, it'll begin to divvy up the work, maybe do some of them serially. So fascinating, fine. This can be helpful, but you can run into other issues. So there are actually also ways for us to use our entire cluster to do this grid search. And so there comes a time where you're like, how am I gonna find an image that's distributed model fitting? And that time then takes you to bigdatapics.tumblr.com, which is one of my favorite image websites. Everything is blue and in binary. And it looks like the space age future. So what we're gonna do here is, instead of running all of this grid search model fitting on a single node with a single Python interpreter, we're going to actually do this with many nodes, many processes working simultaneously. And relatively recently, there was a package called Spark scikit-learn that came out. To use Spark scikit-learn, you need to install it on your driver node, and you need to install it on your cluster. And then what it'll allow you to do is not automatically scale up model training from a single node to the entire cluster, but instead do this sort of grid search where, instead of having to do 1,000 model trainings with slightly different parameters, to farm this out on your cluster. And so what we've done here, that's a change from this one, which is the serial model fitting. The only thing that we're going to change is the import at the top. Oh, I was like, why is this really not going to where I needed to go? And I realized I was going in the wrong direction. So we're going to change the import at the top from scikit-learn grid search CV to Spark _scikit-learn. Great. The code doesn't change at all, and it will just do all the work we need. Fantastic. I'm actually kind of thrilled by that project. I think it's a great idea. It's incredibly useful. And making the distinction between massively parallel model fitting, where you're making one model, versus massively parallel model fitting, where you're making tons of models with slightly different hyperparameters. It's good to be precise about that, because I think the value of this grid search parallelism is actually pretty immediate and fits into people's workflows pretty quickly and easily and obviously. So we then have distributed model scoring as another way that Spark can fit into our machine learning workflows. Again, model scoring, model deployment, it can mean so many things. We're assuming we've written a model somewhere and that we're then going to apply it to some kind of data. So let's suppose we're going to apply it to some kind of data with a REST server. Well, we can imagine that the data that we're coming in is getting transported with an HTTP request, and that we're going to respond with an HTTP response. And there is actually a really wonderful library called OpenScoring, which will allow you to spin up a REST server very easily that has REST endpoints predefined deploy your PMML models to it, and then do all of the request understanding and response giving that you need it to do. And so this is a description of some of the REST endpoints that exist. So you can deploy models using post and put. You can do model prediction in batch, so you can give it a bunch of JSON blobs that represent a bunch of features, and it'll give you a response back. Awesome, fantastic. So that is a type of deployment system. When we get to actually wanting to apply this to a huge database, sometimes people want to keep this REST server up and send HTTP calls and get responses back and use that to write the output of the result. And that's one method of deployment that seems pretty flexible, but big data is just another word for DDoSing your own systems. So again, this is one of those ones I had a really good time trying to find images for. I really don't want a keyboard with my own DDoS button. So if you have a very large table that you're trying to apply model predictions to, what you will find is that you'll pretty quickly overwhelm REST servers like this. And so any single point of any single point of contention will become an issue. So instead of doing this, what should we do with this model that we've stored hopefully in PMML? Well, a lucky thing for us is that there's a system called JPMML. I don't feel like there's enough acronyms in this talk. There's a system called JPMML, and JPMML allows you to load a PMML file and then has all of the corresponding Java classes that knows how to apply it given the parameters that are fit in your file. So the way you would use it is something like this, where you say, hey, I'm going to load this PMML file. Let's build this transformer. You have a little factory that builds a transformer for you, and then you can call it in your code. So this is something that would be relatively easy to use inside of Spark, because Spark is JVM-based fundamentally. And you can then take a PMML file that you've written somewhere and apply it regularly using JPMML, perhaps nightly, weekly, run it as a cron job. So hopefully what we've seen here is that there are a variety of machine learning workflows that generally follow this description of you do model training, and model training is defined kind of vacuously as the thing that connects data to this model that you output. And then once you output that model, you need to persist it in some sort of sane way. Given your form of persistence, you might be able to then apply it to new data that's coming in. And there are 3 ways that I've seen that Spark realistically fit into this workflow. The first is with distributed model training. The second is with distributed grid search. And the third is with distributed model application. And so working on a cluster can happen at a few different stages, and there's different trade-offs and benefits to both of those. So with that, thank you very much.